I made this up as a sort of a choose-your-own-adventure of questions. Notice on the left I have find the zeros of, find the x-intercepts of, find the roots of, factor the following completely. So you could pick any of these four stems and put it with any of these. So imagine you are doing 1a, find the zeros of f of x equals x squared minus x minus 6. And I created these problems to highlight sort of three different approaches. So if I saw something like this, the approach that I would use is factoring. I'd say, I think I can factor that. So for a, let's imagine I was doing 1a, okay, and I was trying to factor. I'd say f of x equals, let's see, x squared minus x minus 6. I'd like to set that equal to 0. I'd like to use the zero product property, so can I write that as the product of two things? Well, those two things need to have a product of negative 6, but the sum needs to be negative 1. So two things that multiply to negative 6, how about a 3 and a 2 with one of them negative? I want the thing to come out to negative 1, so let's make negative 3 positive 2. You can see if you multiplied all of that out, it would come to that. X equals negative 2 would make that 0, making this true, or x equals 3 would make that true. So these are my zeros. Now if you were doing problem 2a, you would say the x-intercepts are, say, negative 2, comma, 0, 3, comma, 0. Those are points where you intercept the x-axis. The roots, you could say, are x equals negative 2 and x equals 3. If you want to factor this completely, well, you could say f of x equals x plus 2, x minus 3. That's called a complete factorization. Okay, so on to the second. Now this, you notice that might be hard to factor. I'd have to distribute a bunch of stuff. This actually is already made into a perfect square, so you might call this method perfect square, or maybe I'll call it complete the square. And isolate x. So if the square weren't completed, I would have to complete it to do this method. But let's say I'm doing 1b, so find the zeros of g of x being equal to negative 2x plus 1 squared minus 4. Since that's already got a perfect square in it, I would set that equal to 0. But instead of trying to factor this side, since x only shows up once over here, what I would do is I'd try to isolate the x. So adding 4 to both sides, then dividing by negative 2. This is a little deceptive. 4 divided by negative 2 happens to be negative 2, x plus 1 squared. Now I'm going to take the square root of both sides. Square root of negative 2 equals x plus 1. The plus or minus goes outside, and you might say, I'd really like that inside negative to somehow work with that outside negative. Well, it doesn't. Sorry. The square root of negative 2 is not a real number. That's an imaginary number. What does that mean? That means you have no real solutions. If you wanted an imaginary solution, you could subtract 1, and you'd get negative 1 plus or minus the square root of 2i, I being the square root of negative 1. But typically when we're trying to graph that, we would say no real zeros, or no real roots. And of course on the xy plane it has no intercepts. Okay, now you could actually go back here, and if you were adept at finding, notice the vertex is at -1, -4, and with A being negative, this is concave or cupped downward, and you can see that it never actually crosses the x-axis. But if you didn't see that, you were just so gung-ho to do this, you'd get down here, you'd say I have a square root of a negative, no real zeros, no real roots, no intercepts, and if you were trying to factor it completely, you really couldn't factor it into two linear terms like that. All you could do is multiply out and factor a constant. So, for instance, notice I'd have -2 x squared plus 2x plus 1 minus 4, and then my complete factorization here would just be -2 x squared plus 2x minus 1. That does not factor. Okay, so let me make sure I did that right. No, I didn't. If I factor -2 out of there, that should be a +2. So 1 plus 2. Got to be more careful there, is +3. So that should multiply to -6, and then if I distributed all of that, that should be -6. Okay, so on to the last kind of problem. Let's imagine that you couldn't figure out how to factor that, and that you didn't want to complete the square, which you could, and isolate x. Well, we have a third strategy, 1, 2, 3, and the third is using the quadratic formula. Okay, so we're going to take that h value up there, 1c, and we're going to use h of x equals 2x squared plus 3x plus 1, and I'm going to use the quadratic formula here, so it will be equal to 0 exactly when x equals -b plus or minus the square root of b squared minus 4 times a c all over 2a. Okay, so that comes out to -3 plus or minus the square root of, let's see, we have 9 minus 8, so that's the square root of 1 over 4. Now, this might be a little deceptive because in my wonderful world here, the square root of 1, of course, comes out as an integer. There is absolutely no guarantee that that's going to come out as an integer, but it makes my problem a little easier, so perhaps you can see what I'm doing here. We have, let's see, -3, -1 is -4 over 4. -3 plus 1 is -2 over 4. So those solutions, these are x values. These are x values that are zeros. You could write as x equals -1 or x equals -1/2. Okay? If you were trying to write them as x-intercepts, -1, 0, -1/2, comma 0, and so on. I think it's worth mentioning how you would factor this completely with that information. If you take these values, whether they're integers, rational numbers, irrational numbers, what you're going to do is you're going to say this is 2 times x minus the first solution. The first solution is -1. X minus the second solution, -1/2. So you could actually double check that 2 times x plus 1 times x plus 1/2 is what actually equals that. But you might not have ever been able to see that this factors as 1, 1/2, and 2. So this is a real powerful technique. It'll also tell you if you're taking the square root of a negative number for sure when you have no real solutions.